Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying application of derivatives lecture 3. In this lecture we'll be talking about shortest distance between two curves and also we'll be talking about monotonicity. Okay. So let's begin our lecture with the shortest distance between two non-intersecting differentiable curves. So let's say we have these two curves over here. Okay. Now, what should be the ideal thought process to find out the shortest distance between these two curves, right? So what we can do, we can start with a particular point and start dropping lines, right, to see which one is the shortest. So you can see that the distance is reducing and now it's again increasing. So what we can say that distance is minimum for this one and it seems to be perpendicular to the other curve, right? So these lines, this one, this one, this one, this one, this one, these were not perpendicular to the curve, so that's why they were a little lengthier. But this one, this particular one which is perpendicular to the other curve, that is the shortest, right? Now we can do this activity for different points as well. So let's say if I do this activity for this particular point, I get a line like this, right? Now we can see that it's perpendicular to both the curves and it's shorter than this one. So we can say that when the common line is perpendicular to both the curves together at the same time, in that case, that is the shortest distance, right? That would create the shortest distance. So alternatively, what we can say that at this point, we are drawing a tangent. At this point we are drawing a tangent and then we are finding out the distance between these two tangents at this particular point. Okay, so this is the way we have to find out the distance between two non-intersecting differentiable curves, right? Shortest distance. So let's see that in an example. Find the shortest distance between the line y equals to x minus 2 and parabola y equals to x square minus x square plus 3x plus 2. Okay. In this case, we have been given a straight line and we have been given a curve. Okay. So what we have to do, we have to find out a parallel line. Why? Because in that case, what we were doing, we were finding out the point where this line was becoming normal to both the curves, and after that we were finding out the tangent at those points and then finding out distance between them. This is what we were doing, right? So in this case this line is there, so we have to find out a parallel line to this particular line, so that would give us a point and then we can find out the distance, right? Simple. So the line over here is y equals to x minus 2. So in this case, we can compare it with y equals to mx plus c. That gives us slope as 1, right? So the given slope of line is 1 and that should be the slope of tangent to this curve as well, right? To find out the shortest distance. So we have y equals to x square plus 3x plus 2. So to find out the slope at a particular point, we have to differentiate it. So y dash would be 2x plus 3. Now we know that y dash at that point was 1 because it was parallel to this line, right? So this would give us 2x equals to minus 2. That's why x equals to minus 1, right? We have got 1 point over here. Now if we have got x equals to minus 1, we can plug that value over here and we'll get the y value as well, right? So y would be minus 1 square plus 3 times minus 1 plus 2. That comes out to be 0, right? This is 1, this is minus 3, this is 2, that comes out to be 0. So we have got the point x comma y on the curve, that is minus 1 comma 0. Okay. So ultimately what we have got is, we have got this straight line, we have got this curve, we have got this point where we have to find out tangent, and that point is minus 1 comma 0, and this is our tangent. And what we have to find, we have to find out this distance between these two parallel lines, right? How do we do that? So we have to drop perpendicular from this point and we can use the straight lines formula to find out this particular distance, right? So that formula is, let's say this point is h comma k and we are dropping a perpendicular on line ax plus by plus c equals to 0. How do we do that? This distance d. So this distance d is equals to a times h plus b times k plus c divided by under root a square plus b square modulus, right? This is the distance formula. So we'll be utilizing this formula to find out the distance from minus 1 comma 0 to that line, right? So that line is y equals to x minus 2. So we can write that as y minus x plus 2 equals to 0. Okay. So d would be modulus of y is basically 0 minus of minus 1 plus 2 divided by under root of 1 square plus minus 1 square, 1 square plus minus 1 square. So this would be d equals to modulus of this actually becomes 3 upon this one becomes root 2. Okay. So 3 by root 2 is the answer, right? Now let's talk about monotonicity. Okay, so this comes from the word monotonous, that basically means showcasing a repetitive behavior, right? Now in this case, mathematically, that means it's either increasing or decreasing. Basically it's just increasing, it's not falling down, and in this case it's just decreasing and it's not going upwards, right? So it's showing a particular behavior, that is it's just going up, and in this case it's just going down. That is the kind of behavior it's showing, right? Same kind of behavior. So that's why these functions are called as monotonic functions. Okay, and now let's define monotonic functions formally. Okay, so the first thing to notice over here is these functions need not be continuous and differentiable, right? Doesn't matter. Okay, so let's say we have this example. You can see that this function is not continuous and not differentiable, but it's still increasing, basically showing a monotonous property, right? Now, broadly speaking, we can categorize these functions into two parts, either increasing or decreasing, right? Either of this type or of this type, right? Whether differentiable, non-differentiable doesn't matter, but broadly we can categorize into two parts, increasing and decreasing, right? Now, if we talk about just increasing functions, we can further subcategorize this increasing function into two parts. The first one is strictly increasing. Second one is just increasing. Now, in case of differentiable functions, we'll further subcategorize this increasing into two parts, but that's for the later part. As of now, we have broadly divided into two parts, strictly increasing and just increasing. Now, if we talk about strictly increasing, the graph would look like something of this sort. This point is, let's say, x1. This point is, let's say, x2. And let's say the function is fx. So this is f of x1, and this comes out to be f of x2. Now, given that x2 is bigger than x1, we can imply that f of x2 is bigger than f of x1. So this is the property of strictly increasing functions. If x2 is bigger than x1, in that case, we can say that f of x2 would also be bigger than f of x1, right? That's the main property to how to define strictly increasing functions, right? You have to remember that. Now, if we talk about increasing functions, in that case, you can have a graph like this one, where we can have a plateau. Okay, it might look like something of this sort. We can have a plateau, right? Basically at this particular point, or at this particular point, let's say this is x1, x2, we can see that the values are not changing. So at some point, values can stay stagnant in case of increasing functions. Now this definition may change from book to book. I'm not saying this is the perfect definition. You will find different definitions in different books, or maybe in different videos. But in the examination, you'll have to judge from the options that what kind of definitions and answers they're expecting from us. So these definitions may vary from book to book or videos to videos, but the overall summary is similar. Overall summary is similar, and you'll be able to make out from the options that, okay, this is the kind of concept they're expecting from us. Okay. So until now, we have just talked about the increasing part. We have to also include the decreasing part as well, right? So for that, we again have two categories. So the first one is strictly decreasing, and second one is just decreasing. Now in this case, we have a function like this. Okay, so let's say this point is x1, this point is x2. So this value would be f of x1, and this value would be f of x2, right? Now in this case, if x2 is bigger than x1, that means f of x2 would be less than f of x1. This is how we formally define a strictly decreasing function. And now if you talk about just decreasing functions, in that case, we can have a flat line like this. Okay, so let's say this point is x1, this point is x2, this value is f of x1, and this value is f of x2, right? Now in this case, we can say that when x2 is bigger than x1, when x2 is bigger than x1, that implies f of x2 is less than equals to f of x1, right? Note that inequality, right? It can be equal as well. We have seen that we can have a flat line. So that's why it's just not less than f of x1. It can be equal to f of x1 as well. Okay. So when x2 is bigger than x1, f of x2 is less than equals to f of x1. In this case, when x2 is bigger than x1, f of x2 is strictly less than f of x1. Okay. And now let's talk about a special case of differentiable functions. Previously, we had a broader categorization into strictly increasing and increasing for the generic case for all sorts of functions. But this one is differentiable, right? So that's why we have further subdivided increasing functions into two parts. Okay. So we have the first major category is strictly increasing, that is the same as previous one, and the second category increasing is divided into two parts, that is increasing and non decreasing. Same kind of definition, but just we are talking about special case of differential functions, that's why we have these three categories. Okay, now let's first talk about strictly increasing. So the first definition is same as the previous one. We have x1 over here, we have x2 over here, and for x1 we have f of x1, and for x2 we have f of x2. Okay, now when we say x2 is bigger than x1, that implies f of x2 is also bigger than f of x1 in case this function is increasing, strictly increasing. Okay, strictly increasing, that means f of x2 is bigger than x1 given that x2 is bigger than x1, right? That was a basic condition. Now this can also be written in terms of derivatives. Okay, we can see that slope of this curve is always positive, right? We can see that it's always increasing, it's not even flattening out, it's always increasing. So that's why our other condition is f dash x is bigger than 0. That is specially applicable for differentiable functions, right? Either this one or the previous one, that was the basic one, and since this is the differentiable function, that's why this is also applicable. You can use either of them. Okay, now if we talk about just increasing function, that is the second category, right? Now in this case, what is happening, function would more or less look similar to the first one, but there would be a single point where f dash x would be 0. Okay, but that would be just a single point. At this point f dash would be positive, at this point f dash would be positive. So at any point f dash is positive except for one single point. That is also a possibility, right? So that means our condition over here would be f dash x should be positive or equals to 0, right? But that equals to 0 is coming at a single point, it's not coming for an interval. It shouldn't be like f dash is 0 over here and over here as well. Okay, so it shouldn't be like in this particular range f dash x is 0. It shouldn't be like, it should be at one single point. So if that is happening at one single point and on the vicinity of that point f dash is positive, then we can say that the function is increasing function. Okay, now comes the third category, that is non-decreasing. So for this one f dash x was positive, this one f dash x is greater than equals to 0, but 0 is not for interval. And the third condition is, third case is where function might look like something of this sort. It's not falling down, but we can see that f dash is 0 for an interval, right? For this particular interval f dash is 0. So again condition is same, f dash x should be positive or equals to 0, but in this case we have the intervals as well. Okay, we have these intervals where f dash can be 0 for a prolonged period of values. So if I were to summarize it once again, so this one is having f dash as positive, second one is having f dash as positive or equals to 0 where f dash is 0 happening at a point and not an interval. In third case, this is also the same condition, f dash is positive and 0, but it can happen for the interval as well, right? The f dash 0 can happen for the interval as well. Okay, and now if we talk about the second types of function, that is decreasing types of functions. The first major category would be strictly decreasing, second would be just decreasing, third would be non-increasing, right? Now in this case, in the first case, condition would be f dash x should be less than 0. In this case, f dash x should be less than equals to 0, where f dash x equals to 0 can happen for a point, not for the interval. Okay, in this case f dash x also less than equals to 0, but over here f dash x can be 0 for an interval, right? So over here no interval, here it can happen for interval. Okay, now let's talk about monotonic functions at a point and interval as well. This is missing from here. Okay, so let's first talk about the point. Let's say we have a function like this. Okay, and this is the point we're talking about. Let's say this point is a, and these are the vicinity points over here. This is a minus h and this is a plus h. Now you can see that this is an increasing function, right? This is a strictly increasing function, you can see that, right? In this case, if the function is increasing at a, what are the conditions? F of a plus h should be bigger than f of a, That is first condition. Also, f of a is bigger than f of a minus h. Now this is the basic most condition for any sort of function, differentiable, non-differentiable, discontinuous, any sort of function. This condition has to be taken care of, right? That is the basic most condition. Now in case of differentiable function, we can further write down this category, this condition as f dash a is positive. In case of differentiable function, this and this implies the same. They are the same thing. But in case of non-differentiable function, you have to use this particular condition. Okay. If this condition is being satisfied, then we can say that the function is increasing at this point. And if this condition is satisfied for a differentiable function, we can say that this function is increasing at this point, right? So both means the same for differentiable functions, but this one has to be used for any sort of function, okay? And now if we talk about the second category, that is monotonic functions in an interval. In that case, it becomes a little more interesting, right? So let's say we have a function like this. Now we can see that this is increasing and then decreasing. This is decreasing and decreasing. So overall, this function is non-monotonic, right? Because it's not having a single property. It's having multiple properties. It's increasing and then decreasing, then increasing, then decreasing, right? So it's not monotonic functions in general, right? But what if I just take this particular interval, right? I'm just talking about, let's say this point is x1 and this point is x2. Now in this interval, we can say that this function is monotonic. So for this particular function, we can say that this function is monotonic in this interval. For example, sin x, right? If you talk about sin x would look like something of this sort, right? So this would be pi, this would be pi by 2, this would be 3 pi by 2, and this would be 2 pi, right? This is 0. Now if we talk about this particular portion, 0 to pi by 2, in this case we can say that sin x is also monotonic or increasing, right? From pi by 2 to pi, we can say that sin x is decreasing or monotonic, right? But in general, is sin x monotonic? No, it's not. It's monotonic for a particular interval. So that's why it becomes a little tricky over here, right? So if you talk about non-monotonic functions, we have seen the example of sin x, right? You can see that in general, this function is not monotonic. It's not having one singular property. It's changing its property. It's changing its gears, right? That's why it's non-monotonic function. And now let's solve this example. We have fx equals to x square minus ln x. And what do we have to find out in this example? We have to find out the intervals where this function is strictly increasing or strictly decreasing, okay? Now we know that x square is differentiable, ln x is differentiable, so we'll be using the second method basically for differentiable functions, right? So let's first calculate the derivative over here. So f dash x equals to 2x minus 1 by x, right? Now how do we know if the function is strictly increasing or strictly decreasing, given that we have find out the value of f dash x, right? So we check the sign of f dash x. If f dash x is positive, in that case we say that the function is strictly increasing. If f dash is negative, in that case we say if the function is strictly decreasing, okay? So this would become 2x square minus 1 divided by x. It can be written as root 2 x minus 1 root 2 x plus 1 divided by x. Now remember wavy curve method, right? We can find out the value, basically sign of this function with the help of wavy curve method, right? So we have these following points: minus 1 by root 2, 0 and 1 by root 2. Based on the critical points, for this critical point is 1 by root 2. For this critical point is minus 1 by root 2. And for this critical point is 0. So that's why we have marked this one. Now this would be plus minus because it's in the standard format, right? Now we can see that the positive region is the one where function would be strictly increasing, and negative region is the one where the function would be strictly decreasing, okay? Over here, simple. And now let's solve this last example. Separate the intervals of monotonicity for the function fx equals to 3x raised per 4 minus 8x cube minus 6x squared plus 24x plus 7. Okay. Now we can see that this is also a differentiable function because it's polynomial function, right? So we'll be using the same method. So f dash x, that would be 12x cube minus 24x square minus 12x plus 24. Okay. Now we have to find out the signs of f dash x based on which we can separate the intervals, right? So we can take 12 as common over here. This would be x cube minus 2x square minus x plus 2. Okay. Now, if we take x square common over here, so we'll be getting x minus 2. If we take minus 1 common over here, we'll be getting x minus 2, right? Now this becomes 12 times x square minus 1 multiplied by x minus 2, right? Now this is 12 times x minus 1, x plus 1 and x minus 2. If we go by the wavy curve method once again, what are the critical points? 1, minus 1 and 2, right? So this is minus 1, 1 and 2. So plus minus because it's in the standard format, right? I can see that this particular interval is for the increasing type of function, and this particular interval and this particular interval is for the decreasing type of function. Okay. Now, one interesting thing over here about the intervals. Let me remove this. Now, let's say I'm saying the intervals would be minus 1 to 1 union 1 to 2 to infinity. For increasing type of function, that would be wrong. Although it looks like that, okay, this is minus 1 to 1 and this is 2 to infinity, but that would be wrong, because when we are saying along with union, that actually means this is an entire set. This is a part of a single set, right? This is what we mean by union, right? That these two are a part of a single set. And now if we take two values from this entire set, let's say I'm taking one from this particular range, that is 0, and let's say I'm taking one from this range, that is 3. Okay, I'm taking these two values from this entire set, right? And based on this notation, our function would look like this, right? This is 1, sorry, this is minus 1, this is 1. From minus 1 to 1, it's increasing, strictly increasing. From 2 to infinity, it's also strictly increasing, right? So this representation is correct. But what if at 0 the value is somewhere over here, and at 3 the value is somewhere over here? You can see that this value is bigger than this one. But based on our original definition, we say that when we are defining a particular range for the strictly increasing function, we say that if x2 is bigger than x1, that should also mean fx2 should be bigger than f of x1. But over here, what is happening at 3? The value is lower than at 0. Although 3 is bigger than 0, but what is happening? F of 3 is smaller than f of 0. And that's not complying with the basic definition, basic root definition, right? That's why you'll not be writing union in between. This is one separate interval, this is one separate interval. In both the intervals, individually, the function is strictly increasing, right? So let's end this lecture with this example, and we'll be talking about minima and maxima in the next lecture. So let's meet in the next lecture. Thanks for watching.